Yeah, good morning all. So welcome to the session, second day of workshop on AI techniques for power system problems. So Balaji Institute of Technology and Science organizing this webinar. This today's workshop on pantechelearning YouTube channel. So we people yesterday discussed about the fuzzy system and artificial neural networks, right? So here we people design the fuzzy basic system, right? Look at here, everyone. I think everyone visible, right? My screen visible, right? All of you. You can see here. Now this is the command window, and here we created a subsystem. So then here we created a one system, right? So that is speed FIS file. So while we are creating the file, if you observe here, this is in FIS file, right? Speed FIS. FIS file. Then how we need to optimize or how we need to get the same results in the Simulink model, MATLAB Simulink model, how we people will get the results exactly. So here we have several options are there to open the Simulink directly. You can see here Simulink. If you click here Simulink, then enter means MATLAB Simulink will be open. You can see here, if you double click and enter here, Simulink library will open. Simulink library will open here. So once we are opening the Simulink library, the same FIS. Now you can see here, it is initializing MATLAB Simulink. Here we are trying to open and it is initializing. So then whatever the fuzzy file yesterday we created, the same fuzzy file, we will take the data, whatever the rules we created here, the same rules we need to take to the Simulink model. This is the Simulink here. This is Simulink model. So here I took, you can see here, this is a Simulink model. So first here I took a new or blank model. A blank model here I taking. Here the blank model I am taking. So then one new untitled file will be created here. So after that, we need to go to the fuzzy logic toolbox. So from the fuzzy logic toolbox, we need to design our model. Now you can see here, this is the untitled file, a new file which we taken from the Simulink. So now you can see here, you can see here. So this is the new file which I took here. So everyone visible, right? You can see here. So this is the library browser. So we can double click here. This is a library browser. So library browser will open. From the library browser, we will take the in blocks from the inbuilt blocks we will take. So from library browser here, you can see here. So from library browser here, we have fuzzy logic toolbox. Look at here, fuzzy logic toolbox here we have. So from the fuzzy logic toolbox here, I took this file. You can see here. So the fuzzy logic toolbox, fuzzy logic controller here I took. Fuzzy logic controller here I am taking. Fuzzy logic controller here I am taking. You can see here. So while you are taking the fuzzy logic controller, go to library browser. So then here from commonly used block, you can see here from commonly used block, I will take a scope. I will take a scope here. I will take a scope here. You can see here. So then from library browser, sources, from sources, I will take a step block. So this is a step block which I took from the library browser. Now you can see here. So by taking the step block and fuzzy logic controller, so then what I'm doing here, now in this fuzzy logic controller, we need to give the, what is the fuzzy file name which we given here? You can see here, FIS name we need to give here. So now here, if you see here, so then speed.fis file here we give, right? Speed.fis file. So here I am giving speed.fis. Speed.fis. Okay. So then apply, okay. You can see here speed.fis here we given, apply, okay. So then here actually input, what the input we taken yesterday? So here step time here I am taking 0.2 second and the initial value and the final value. So here the speed of the motor here I am taking 800 to 1200. This is the range here I am initially. This is the input, right? So then now if we run the simulation, you can check here. If you run the simulation, what will happen? You can see. So now here we are getting some error, right? So whenever we can see here, error evaluating parameter FIS. So untitled fuzzy logic controller. So here we need to train the system actually, the fuzzy logic controller, what is the error here we are getting. So now you people can go to the command window. You can go to the command window, then enter here fuzzy. Fuzzy you need to enter. So then enter here. You will get the pop-up here. Fuzzy logic designer pop-up you will get here. So file, import from the file. You can see here. While you are entering the fuzzy, you will get this pop-up. Go to file, import from file. Okay. So here speed, right, which I took yesterday. So this file you can open it. This file you can open it. Mamdani type, right? Speed. So then file, export to workspace. Export to workspace. So now you people can go to the untitled file. You can run it here. Now you can see here. File, export to workspace. So in this fuzzy logic controller, here we are getting the error, right? We can see here, file, export to workspace. So then you can run the simulation. Now error clear, right? So here you can observe here, we people are given the range, speed or step block, the 800 to 1200 voltage, speed of the DC motor we given. So then you can observe here. You can see what is the voltage. The voltage range you can observe here. How much? At 0.02 second, then 800 to 186 near. You can see here the graph. You can observe here the Simulink. So MATLAB, it is graphically we can analyze the program. Graphically we can analyze the entire program. So now you can see here. I'll change the parameter settings here. Apply. Okay. Okay. So if we change here, whatever the data we created yesterday, the same data if you see here. So when you are entering here, and if you run the simulation, you can see here. This is the voltage range actually. When you people are running the motor in low speed, while you are running the motor in low speed, 20 and 60 in between the range, if you are driving, if you run the motor, then this is the. So now the same fuzzy logic controller, how we can implement in the power system network or power quality problems. So to improve the power quality, how this fuzzy logic controller will help, how this fuzzy logic controller design will help our power system problems and power quality problems. This is a basic example for understanding the DC motor. For taking a simple DC motor, so then here we designed this one and we run the simulation, right? I think you people are understood. So here we check the simulation already in the command window. So then here you can see here in the Simulink also we verified here. Okay. So now yesterday The power quality problems. To improve the power quality, we have different type of fact devices are there. So by using those fact devices, so from either active power filter or shunt active power filter or DVR, dynamic voltage restoration, and we will get the unified power quality conditioner, unified power flow controller, and IUPFC. So inter transmission line unified power quality conditioner. Whatever the device, whatever the factor device, yes, either in distribution side or transmission side, it may help to overcome the problems. So whatever the problems we are getting while we are discussing the artificial neural network or fuzzy logic controller, those techniques for the stability, to improve the stability of the system and to reduce the harmonics of the power system network and to give the quality of the power to the load side. So the consumers, they need the quality amount of the power, right? So while we are taking the power supply from the distribution side, if you are not getting the quality amount of the power, then it will affect on your loads, right? So definitely we need to prefer the quality amount of the, whether it may be 230 or 440 voltage also, we RMS, whatever the AC we are getting to our home or industrial or agriculture purpose application. So in all the domains, we need the quality amount of the power. So how we are getting the quality of the power, how these active power filter or shunt active power filter in the power system network, it is helping to improve the quality. To improve the quality, how it is improving, let's see here. You can see here shunt active power filter. So here in this session, we will discuss about the entirely shunt active power filter. Then I will give one small example for system performance about the how a system by using the artificial neural network with the feed forward neural network. So how we can improve, we will see. So now you can look at here. This is the in distribution side. We can see here. This is 220 VRMS. Here we took. So all these inbuilt blocks which we are taken from the library browser only. So now you can see here from the Simscape, power system, specialized technology, fundamental blocks. So from here, I took a electrical sources. From the electrical sources, so then here a 3-phase programmable voltage source is available. You can see here. So this in MATLAB, MathWorks people, they are providing some inbuilt blocks. So for your particular solution, how you people are effectively utilizing those inbuilt blocks, whether neural network toolbox is there, fuzzy logic neural network toolbox, according to our requirement. So we need to take all the inbuilt blocks. So then we need to implement our project here. So you can see here. You can see here. So this is a power system network. For simply, I will draw a simple network here. Block diagram I will give. You can see here from the source side to we people are sending the power supply, right? From source side to we are sending the power supply to the load side. To the load side. From here, whatever the loads may be, whether it may be linear loads or non-linear. This is the load actually. You can consider or you can take whether it may be linear load. Two type of loads are there, linear load and non-linear load. So while you are working on or if you are taking or if you are preferring the non-linear load, if you are preferring the non-linear load, definitely power quality problem. So here you are sending the AC supply, right? So then if you need the quality amount of the in this system or in this power system network while you are transmitting through the some conductor transmission lines only people will send the power supply, right? So if any case, if in case, so then the problem will occur, whether it may be voltage sag. These problems, sag or swell or harmonics or voltage striking or voltage restriking. So here within the fraction of the second, while you are getting the power supply, sending the power supply like this sinusoidal, so within the fraction of second, the power may interrupt. So after that, it will go like this. So within the 1 to 2 fraction of second, the fault may occur. So this one we can keep, this one we can call it as a sag problem. So if you are, while you are getting the continuous power, if any interruption occurred in the power system network, this is the problem will occur within the 0.1 to 0.2 second also the problem will occur. So if you are getting the power like this, continuous power supply, so then suddenly the power is increasing. So why this will happen means like this you will get. So suddenly the power oscillated means, so then this one we can call it as a swell problem. So this swell problem because of the loads which you are using. Normally if you are in domestic application, if you are operating 2 to 3 loads continuously, then if you are putting more burden on the load side, so then the power system network, it will affect some disturbance. So at that point you may get some oscillations also. So here this maybe sag will occur, this problem will occur due to the faults, whether it may be symmetrical or unsymmetrical faults, it will affect on us. It will affect on us here. Symmetrical or unsymmetrical faults may be due to that. It may be impact or it will be effect on the load side, customer side. It will affect. So then how we people will rectify the problem means, so for that reason, we people are using here in the power system network. So now we are interacting or interfacing with the power converters, so power integrated power converter topologies we are implementing. So most of the cases, if you go with the voltage source converter devices also, it will give good solution here. So if you connected to the parallelly, a converter topology. So for this to overcome these problems or harmonics or reactive power. So while you are keeping here non-linear load, reactive power losses will be more. So to compensate the reactive power and to send the active power more, if you need to send means you need to minimize the reactive power. You need to minimize the reactive power. While you are minimizing the reactive power, if you are compensate the reactive power means, then only you can send the quality amount of the power to the load side also. If we are sending more amount of the reactor, what will happen? Consumption of the power will be more in the load side automatically. So the customer will face the burden actually. So to overcome those problems, here we can keep the shunt active power filter and a series. Shunt means parallel converter. Parallelly we can connect one converter, or series also we can connect. In the series connection, we can call it one as a DVR, dynamic voltage restoration. So combination of DVR and a shunt active filter, or StatCom also we can, StatCom, DStatCom, distribution side StatCom. Okay, shunt active or StatCom. The combination of both these we can call UPKC, Unified Power Quality Conditioner, or Unified Power Flow Controller also. Unified Power Quality Conditioner, Unified Power Flow Controller. So these are the things we will work on it. So to a particular problem in the distribution side, so these shunt filters we can utilize. So combination of shunt and the passive filter, hybrid filters also there. So combination of both shunt and passive filter, we can call it as a hybrid filter also. So here this shunt active filter, how it is compensating, how it is sending the quality amount of the power to the load side, and how these artificial neural network or fuzzy logic controlling algorithm, how it is optimizing FL, fuzzy logic controller, how it will help for our fuzzy logic controller, it will help to minimize the ripples. So here across this one, we will keep a DC link capacitor. DC a link capacitor we will keep. So while you are keeping the DC link capacitor here, the DC link capacitor, if you are getting the more number of the ripples, that means suppose the DC link capacitor, you need to initialize the capacitor voltage around 600 or 800. In between, you can keep the DC link capacitor voltage. If you are initializing up to 600 or 680 or 700, so then if you need to this DC link capacitor, it will need to start to 0. So then it will reach us to some peak value. Then it should be oscillated. After some time, it should be settled down. So if you are getting like this, it will be fine. The ripples at after some point, if you are minimizing means, then it will be fine. But if you are getting more number of the ripples like this, if you are getting the ripples here, more oscillations if you are getting at the DC link capacitor side, like this if you are getting, that means these ripples may be 100 or 50% of the ripples like that you are getting. If you are maintaining the 50% of the ripple while you are taking this 600 as a input to this DC-DC converter, so here you are getting some problem. So by using this shunt converter, you are minimizing or you are rectifying that problem. So while you are rectifying the particular problem, so input of the this DC to AC converter, you need to give constant or pulsating DC with minimum ripples, either 10% or 5% of the ripples if you are maintaining means, then it will be fine. Otherwise, it may affect on the power system network again, because while you are converting the DC to AC by taking the DC supply, you are taking as a DC, while you are converting the DC into AC, you need to get like this, right? People, AC means we will expect the pure sinusoidal, but we will not get the pure sinusoidal. So we will get the pulsating AC. So pulsating AC, if you are getting, then again we are keeping the LC filters. So to get the pure sinusoidal waveform. So then how the shunt active filter we are synchronizing with the grid and load side, how it will rectify, what is the Park transformation, what is the synchronous reference frame, what is the instantaneous power quality theorem. So then how the fuzzy logic controlling theorem, it will act as a feedback control technique to minimize the ripples of the DC link capacitor, we will see here. So now you can see here, the entire network people are visible, right? Look at here, this is the entire power system network, and the power quality problems only here we are identifying in the power system network. So you can see here, so 220 VRMS I took here, so then here 220 VRMS only, 50 Hertz frequency I took. So then here you can see here, this is the RLC RL branch. So here the impedance which we taken 0.1 and 0.15 e power minus 3 inductance. So then here we take a bus system. So then here you can see here this one, here you will get the VABC and IABC, right? Source voltage, source current, while you are sending the power through this element or through this impedance while you are sending, then you may get here, you can see here, VABC, IABC you will get. While you are getting the VABC and IABC, so then you are sending to directly non-linear load side, right? This is the point of common coupling point at load side. Load side, point of common coupling point, right? So then the DC link capacitor here you can see here, 35 microfarad here we are taken. So then this one we created a subsystem. So this active filter, how to create a subsystem, I will show here. So look at look at here. So this is the a new untitled file. Here I will try to create a subsystem for the active power filter. Now you can see here. So from the power electronics, here I took a IGBT switch. Here I took a IGBT switch. You can see here controller. So in high power applications, we need to take the IGBT switches. So here you can see. So here people visible, right? So this is S1. You can see here. This is the S1 switch here I took. So then S2, S3, S4, S5, S6, right? So this is the three-phase inverter, right? So here voltage source converter, collector to collector. Here emitter to collector here I connected. Then collector to collector here we connected. So then collector to emitter here we connected. Now you can see here. So this is VA, VB and VC, right? A, B and C. So here I need to give the DC link capacitor or a DC voltage I need to go. This DC, it will convert into a AC, right? So you can see here. So select all here. By selecting the all, right click. So you can see here, create a subsystem from the selection. Create a subsystem from the selection. So now you can see here. These are the gate pulses we need to give. This connection 1, you can see here. So it is in left side. Okay. Connection 5. Okay. So then here, this is positive, right? VDC. So plus VDC. So then here, negative VDC, here we give it. So then these are the pulses, right? Input 1, 2, 3. These are the pulses actually. So what I am doing here, so I will take a demux block. You can see here. So from commonly used block, I will take a demux. So we need to give the gate pulses, right? So double click this one. So take the number of outputs, 6. So here I will give the gate pulse here. Here I will give the gate pulse. So these are switch 1, right? So I will give the name here, pulse 1. Okay. You can see here. While you are, I think most of the people will know about the DC-DC converter, right? This DC to AC converter, how it will operate. So P1 and P2 pulsating to pulse 2. So then here pulse 4. You can see here P5. This one I will take 6 actually. 6. So this is 5 I will take. Okay. So then here what I am doing. Okay. Here I will connect. These are the gate pulses. 3. So 4 and 5, 6. Okay. You can see here. So now this one. So this is VA, right? VA, VB. This is VC head. So VDC, you can check here whether these are in left side or right side. Okay, all are in left side, right? From here, I will take a input port. This input 1, here I am representing here the gate pulses, PWM, pulse width modulation, or pulses we need to give, right? So then you can come back here. If we come back here, so then VA, VB, VC, so these things here, it is in right side, we need to get positive VDC, then this is in right side, negative VDC. So like this you are getting, right? So here you need to connect a DC link capacitor, VA, VB and VC. So for this inverter, 3-phase inverter, you need to get the gate pulses actually. So this is parallelly we are connected to the power system network, right? So you can call shunt active filter. This is a voltage source converter device only. So here you need to connect. Then inside of this, by creating the subsystem, so you can give the name as inside of the top of the subsystem main. So then right click here, right click. You can see here, we got one pop-up, right? Go to mask here. Go to mask, create a mask. Create a mask here. So creating a mask, you can give or you can give the command fprintf. Okay. So then you can use semicolon, SCAPF, fprintf, apply. Okay. So now this is the thing which we taken here. You can see here. This is shunt active power filter, right? So the same shunt active filter here I took. I can see here. I hope you people are got it. So here what we did, DC link capacitor, right? So DC link capacitor, where you have the capacitor from here elements, from elements, you can take the series RLC branch, right click, take it as a capacitor. So here we keep the capacitor value 35 microfarad here we are taking. So control R, you can take here, you can see here. So now this DC link capacitor, it have the capability. So DC link capacitor. So in this DC link capacitor, if you are maintaining the constant DC voltage, DC link. So what our fuzzy logic controller here, when we are applying the fuzzy logic controller here, so it will help to minimize the ripples of the DC link capacitor, because we are synchronizing with the grid and load side, right? So then here we need to give the gate pulses, right? So A, B, C, the same shunt active power filter we taken. So here you can observe here, this is the active filter we taken. And inside of the subsystem, you can observe again what we did here. I will try to explain it. You can see here, up to here, everyone clear? So this is the inverter which we taken. You can see here, this is the inverter which we taken positive, negative terminal. Here the gate pulses. In that place, I keep one DC link capacitor. So here the DC link capacitor I said, right? DC link capacitor. So here we keep a DC link capacitor. So then here we connected a VDC. So this VDC, this is a go to block. So this DC link capacitor, how much I need to keep? More than 600 voltage, around 600 voltage. So here the VDC reference here, if you take 220 VRMS, so if you need the grid set, you can see here. In this case, we are taking the feedback path up to 380 voltage. You can see here 600 or 400, 380 or VDC reference you can see here. So this is the 380 and the VDC, this block which we taken from the here. To avoid the physical connections, here we are taking the go to and from block. Go to and from block here. This is the go to block. This is the go to block. You can see here while you are working and the go to and from block. So inside of the subsystem, if you need to give any connection, you can take the go to block. So then the tag visibility also, if you are giving the connection in the same subsystem means then you can go with the local. So otherwise you can go with the global means wherever you are connected the DC link capacitor, wherever you need the DC link connection for your system. So then you can take it as a global. So by taking the global, you can see here. So the DC link capacitor here, I need to observe the scope of the DC link capacitor. Scope of the DC link capacitor here I can observe here. So then in this active power filter, here we are connected a coupling inductor. I said while you are taking the DC as a 380 DC you are taken, then 220 VRMS you need to reach. That 220 VRMS, it is a single phase supply only, right? So then 380 while you are converting DC into AC, at least if you are maintaining the 220 means that is sufficient. So then while you are converting DC to AC, what I said, we will get the pulsating AC. So but actually what we need a pure sinusoidal waveform. So that's reason here I connected a coupling inductor. Coupling inductor I connected. So the inductance and the capacitance, I think people will know capacitance and inductance. It may help to avoid the coupling inductor. It may help to minimize the harmonics. So then we people will get the pure sinusoidal we will get. But while you are getting the pure sinusoidal, you need to minimize the, you need to observe the THD, right? So you can see here, actually we will get whether it may be single phase means like this we will get pulsating AC. Pulsating AC like this we will get. But if it is a 3 or 2 level or 3 level means like this you will get. But what is the actual sine wave? You need like this, right? You need like this, right? So here, what is the drawback here means? I think you can see here, if you are applying the Fourier transform, you will get one mathematical formula. You can see here, this is the harmonics. So you people need to eliminate the harmonics. We need to eliminate the harmonics, then we can get the pure sinusoidal. We need to eliminate the harmonics. So you can see here, sine wave, here also you can observe the harmonics you people will get while you are converting the DC to AC. DC to AC means you will get the harmonics. So how to rectify that problem means, so here we are connected the one DC link capacitor. So here we are connected. You can see here we are connected the one coupling inductor. It will help to overcome that problem. So then here I took a circuit breaker from the library. You can see here from library browser, here I took a circuit breaker. You can see here we can take the fault or three-phase circuit breakers here we taken. The circuit breaker here we taken. Switching times you can observe here. This one is closed only, three phase A, phase B, phase C we are applying, and 0 to 2 by 50. 0 to 2 by 50. So within the seconds, you may get some disturbance. Actually, in real-time domain, where the problem will occur, we don't know, right? So here we are created the problem. That problem we are overcoming. So in the software or Simulink design and the simulation, we need to create a problem. So while we are creating a problem, so then how we are rectifying that problem? By using the active power filter. So you can see here. So then in the particular area, you will get some disturbance. In that particular second, within the fraction of seconds, you get that disturbance 0.04 second. So then you can connect it to the this by taking this one is universal bridge. So then here you are connected, right? So A, B, and C. So now this active filter and the grid and the load you need to synchronize, right? So grid side you are fixing to 20 VRMS, but where the problem will occur, current harmonics you make it. So that's the reason you can see here. As I said, instantaneous power, instantaneous active power or instantaneous power quality theory, VABC, VABS. So this is the from block, the supply which we taken from the grid side. You can see here, this is the grid. So this here I taken VABC and IABC, right? So then what I'm doing here, instantaneous active power theory, for this one we created a one subsystem. So what happened inside of the subsystem we will discuss. VABC, so then IABC. This is the load side current, you can see here. So from load side I current. So what we are doing, the load side currents and grid side source voltage, we are compensating. We are compensating or we are synchronizing both each other. So then the system become more stable. Even though the disturbance occur at load side, it may not affect. So we are overcoming that problem by using the active power filter here. So now you can see here. So source voltage, load side current, load side current. So how much load side current we don't know. So load side current, source voltage we are compensating here. Now you can see here what we are actually doing. In this one, we are creating a 3x3 system into 2x2 system actually. So Park transformation or Clark transformation. So this is the rotating reference frame here we are applying. By applying the rotating or synchronous reference frame, so then actually for inverter, three-phase inverter, so they are maintaining with here we are using the 120-degree conduction mode inverter only, voltage source converter only we are using 120-degree conduction mode. So that 120-degree conduction mode inverter, in between A, B, C phases, it is maintaining with 120-degree, right? So then you can see here how we are representing these things means. You can see here. This is A, IA. You can consider this is IA. So then IB and IC. Okay. So then here A to B 120, B to C 120. So then again B to C. So if you take from here to here 240, right? So each phase we are maintaining with 120-degree, 120-degree, 120. So then how people are representing here means sine 0, sine theta or omega t, sine omega t, sine in matrix form, MATLAB sine omega t minus 2 pi by 3, sine 120. So then third phase, right? Sine omega t plus 2 pi by 3. This is one phase. So then cos omega t minus 2 pi by 3. So similarly cos omega t plus 2 pi by 3. So IA, IB, IC, we are converting ID, IQ. ID, IQ we are converting. So by applying the synchronous reference frame. So synchronous reference frame. So this is a D and Q. ID, IQ, it is in perpendicular. IQ, ID, IQ. So by using this phasor vector diagram, here we are converting. This is one gain block only, but here we write the three-phase system. Then what we are doing? So VD from the voltage source while you are converting the VABC into VDC. So here actually, if you are working on the mathematical, it's fine. Otherwise, if you are unable means, then you can see here they are providing some transformation blocks also, control and measurements. You can see here measurements, transformation. So then you can observe here alpha, beta. So then ABC to DQ also you can observe here. ABC to DQ. We can say here, by using these blocks, you people will get some idea. So ABC, here VABC we are giving. By using the VABC, DQO we are converting. So DQ transformation. You can see here. So 90 degree behind this one. So Park transformation or Clark transformation, we can call this one. So now you can see here, this is the vector actually which we are taking. Inside of this 2 by 3. So actually each phase you can see here, and alpha beta to DQ. So here VD the same way, here currents you are converting. So 100 1 square root by 2 square root 3. So 2 VD VQ you are getting from this one. Okay, 1 by root 3, 2 by root 3 will sine cos theta, cos 0, cos 120, cos 240. How much you can calculate? Cos 120, cos 240. Similarly, sine 0, sine 120, sine 240. So those mathematical representation here we are given. Then VDQ, IDQ. So then what we are doing? This is a mux block, right? Then mux block is which we taken. So then what? Direct access, and you can see here direct access and both current VDQ, current IDQ and voltage VDQ both combining. From this we will get one equation, right? U of 1 represent with the U of 3 plus U of 2 star, U of 4 here we are representing. Similarly here you get the active power here. Here you will get the active power, power P, active power. Q means representing with the reactive power, here you are getting. So by using this active power and reactive power, instantaneous active power theorem we are getting, right? So then VDQ directly here you are giving. Then the losses, what are the losses before the filter, after connecting the feedback? You can see here, here we are minimizing this one. So then before the Butterworth or second order low pass filter, here we are taken. So by using this losses before the filter, after the filter, you can observe here. You can observe here. So then compensating, how we are compensating the Clark transformation, you can see. What are the losses we are calculated? Reactive power and the VDQ transformation. So then you can see here compensating D-axis current, compensating quadrant axis current. So by compensating the DQ theorem, then again inverter, how many switches are there? 3. So total number of switches 6, right? So those 6 switches need 6 gate pulses. So that's the reason again while you are giving the gate pulses, DQ transformation to ABC again you are converting. So inverse Clark transformation here you are applying. Inverse Clark transformation here we are applying. So by applying the inverse Clark transformation, here we may get compensating current. Compensating current, the actual current VDC while you are converting AC means you will get one current, right? Active current here IABCA. So this active current or active power filter current, you are taking, comparing both compensating current, actual inverter current you are comparing. So then you are generating the gate pulses here. Now you can see here. By applying the hysteresis loop, I see compensating current. This is the, while you are applying the synchronous reference frame or Park transformation, Clark transformation, you are getting the compensating current. From that, the refer actual IABC you are giving. So then you can see here. Compensating one, then you can see the IABC, this is one. So but you are getting here, right? So how we need to compensate, right? While you are getting the harmonics, so you need to get some feedback path, right? You are getting like this, right? You are getting like this. So that is IABC. But you are compensating current. This compensating current, it will help compensating the losses and minimizing the losses, and you may get pure sinusoidal waveform. So that's the reason we are synchronizing with the grid side here. So then the hysteresis loop here we apply. So this one is a relay block only, not more than that. So 3 legs we have. Inverter have how many legs? So 3-phase inverter. So 3 relay legs. So each leg, while I am connecting here the switches also, you can see here. So total number of switches here, I took 6 switches. So if you are operating the S1 switch, at the same time S4 switch will be turned on. You can't operate both switches at a time. You can't operate both the switches at a time here. So S1 while you are turning on, S4 you need to turn on. S3 if you are turning on, S6 you need to turn on. So all the switches will not operate at a time. So that's the reason each leg here, you can see here. So in this one, each leg, you can see here, we connected a NOT gate. Then here we taken a data type conversion. Switch will turn on and turn off means we will represent with 1, right? Switch on condition 1 we will take. Switch off means we will take 0 condition on. So here the data clock decimation time here we are representing 10 only. Then the switch here we are connected. This switch, it will act as a if else based condition. If the control port, so after within the 10-second control, this is the control port. So then if it is satisfied, this control port, it is satisfied with the upper port. So then it will allow the signal. So that means either 1 or 0. Otherwise, it will take it as a 0 only. So then here, why we are taking the data type conversion? Data type conversion, it will help to get the real world values only. Real world values means only either 1 or 0 only. So any integer values, it will not allow. This inbuilt will block, it will stop the integer values. Then you may get output as either 1 or 0 only. So then here we are connected a data type conversion again. So then we are generating the gate pulses for the voltage source converter devices. Now we created the subsystem. I already shown how to create the subsystem. So then we are given here. So then this DC link capacitor feedback path, how to maintain means, you can see here. This is a DC. VDC, this one, right? VDC. So from here to here, I took a feedback path. So this DC link capacitor to here, we taken a feedback path. So this is the output voltage, how much you need to keep. So here I need to keep the DC link capacitor voltage 380 voltage only. The reference voltage, how much you are keeping. Suppose if you are keeping 600 or 680, how much you are keeping, according to that you may get the result here. So then here, yesterday I said, so 2 parameter values we need to take. So error, change in error. Error, change in, while I'm discussing the fuzzy logic controller. So 2 input, error, change in error. Fuzzy logic controller, here we are taken. This is the error, change in error. So what is the actual value? What is the actual parameter value? DC link capacitor you are giving, right? So that DC link capacitor you need to maintain 380 voltage. That is the concept. So that DC link ripples, if you need to minimize means. So what is the actual error? Yeah, error, how much we are getting? How much you need? So error, change in error. Error, change in error. So then here we taken a fuzzy logic controller from the toolbox. From the toolbox here, fuzzy logic controller toolbox, you can see here. Fuzzy logic toolbox, we taken the fuzzy logic controller. So then from this, we are getting the KP and proportional integral value. So why this fuzzy and PI controller? It will help to minimize the steady state error value. It will help to minimize the steady state error value. So then here we are given to this one. The fuzzy logic controller and the losses, what you are getting, actual losses we are getting. So the output power here you are get, right, after oscillating the converter. So then here you are getting compensating current, you are overcoming the losses. So let's see what are the rules and how many rules we created here. And here 3-phase rectifier, this is the 3-phase rectifier, a non-linear load which I took here. A non-linear load I took here. You can see here 3-phase rectifier, non-linear load here we taken. So then you can see here. You can see here. You can see here. So now here already we created the rules. So these rules, how to optimize this one. If you run the simulation, we will get the error. So we need to import the data. Whatever the data we created, that data we need to import to the fuzzy logic controller design. So look at here. So the same problem here. The fuzzy logic data you need to enter here. Now you can see here. So we will enter. You can see here. CLC. Clear. CLC. So TS is equals to 50 e power minus 6. Okay. So then here, what I'm doing, entering here fuzzy. So then enter, you will get the pop-up. Pop-up, we will get file, import from the file. Import from the file. So then you can see here, this file here we are imported. So right, error, change in error. How many rules, how many membership functions you can take, you are taken, you can observe here. The membership function, negative gain. So negative medium, error 0, positive medium, positive gain. So we need to minimize the steady state error, right? DC link capacitor, ripples we need to minimize, right? So then negative gain, negative medium, error 0, positive medium, positive. In between -1 to 1, we can create infinity rules. This is the error and change in error. So output also you need to get 2 means. So here we are keeping the KP and Ki parameter values. So then you can see here, file, export to workspace, file, export to workspace here, ALA23 here. Okay, then it's okay. So file, export to workspace. So now here I will show the rules actually, rules, how many rules we created. You can see here, error, change in total number of rules. By taking the 2 factors, you can create 25 rules. So more than that also you can create. Here we created the 25 rules. Here we created 25 rules. Here we created. Okay, error, change in error. According to that, you will get the KP and KI value. Okay, so then file, surface view. You can see the graph also of the about the rules how we created surface view here. So go to the view and observe the surface viewer graph. You can see here. This is the surface view graph here. You can see here. This is the surface view here. So then I will go to here, Shantech to power filter. So now here I will run the simulation. Whether the DC link capacitors we are minimizing or harmonic distortions we will see here. You can see here. It's compiling. Wait a second. It's compiling. Wait a second. Now, so simulation is started to run. So grid side current and the load side current you can observe here. The grid side current and the load side current you can observe in the figure. So whether we are compensating or not, you can check here. The grid side current and load side current, you can check here. Compensating the current, so load side. We can see here, load current, compensating current, you can see here. Visible, right, everyone? So by using the DC link capacitor, the DC link ripples, whether we are minimizing or not, we will see. I will show the DC link capacitor. So it is reaches to some peak value, right? This is the DC link capacitor. You can see here whether the ripples are minimizing or not, you can check. The DC link capacitor ripples minimizing or not. And the variation, otherwise you can observe the variation. How much it is varying. The ripples. So 380 we fixed, right? In between that either 5% or 10%. You can see here. The ripples you can see here 370 to 20% of the ripples 400. Peak to peak you can observe here. You can see here. So then the load side voltage and load side current. So this is the load side voltage and load side current. You can observe here. So three phase grid side voltage around 220, right? We keep load side voltage and the current also you can observe. You can see here. So now you can observe here. Pure sinusoidal and the current only, right? The disturbance where we will get. So grid side voltage we are keeping, our load side voltage also we are getting 220 only, right? 380 DC link voltage while you are converting. You can see here. You can verify here. So then I will show the THD also, total harmonic distortion, how much we are getting. Okay. I can see here. Okay, fine. So regarding this, if you have any queries, you can ask. So apart from this, we have the expert system techniques. I can see here, expert systems also were developed around during the 1960s and 1970s. So these are commercially applied through the from 1980s onwards. Commercially, they are preparing. So it is also called a knowledge-based system or rule-based view system only, and it is a fully computer program that incorporates the knowledge derived from the experts in a specific subject. So to provide the problem analysis to the user. So to the users. And this knowledge is generally stored in one of the many forms like rules, decision rules, and models, and tree and frames also. It uses this knowledge and interface the mechanism to solve the problem which cannot be or difficult to be solved by human skill and intellect. So the common form of an expert system is a computer program containing the rules for analysis and recommendations for the users also. So the applications, so the simply here these expert systems, so it will be depend upon the users. So many applications, these expert system we can use in power system related to the power system designing, analysis, and to match the abilities of the expert system. So apart from this, genetic algorithms, swarm intelligence algorithms, recently teaching based algorithm, water cycling algorithm also they are implemented. So genetic algorithm, it's gives a global technique based on the biological metaphors. So it is an optimization technique based on the study of the natural selection and natural genetics. So here several methods for increasing the efficiency. So in this genetic algorithm, we have several methods to increase the efficiency of the particular problem. So it is the best method for solving the complex and nonlinear problems. It is used for planning of power generation, transmission, and distribution. And here it adjusts the parameters of the excitation to solve the voltage controller, current controller, and reactive power flow compensation also. So fuzzy system, simply we can summarize all the points. Fuzzy system to diagnose the faults. Artificial neural networks means trained to change the values of the line parameters based on the environmental conditions. Depending upon the conditions, we can utilize and we can train the system. Expert system to deploy the outputs as a value of line parameters. Environmental sensors to sense the environmental and atmospheric conditions to provide the input to the expert system. So for more details, you can contact hyd.electrical@pantechmail.com, and you can do WhatsApp 7010888841. So for Telegram, you can subscribe our channel pantechelearning. So once again, for conducting this webinar, I think you will have queries, means you can ask. So for organizing this webinar, we are thankful to the BITS management and BITS College of Engineering and Technology for Narsampet, Telangana. Thanks to the coordinators for Sridhar sir for organizing this webinar, for accepting our invitation. So for more information, you can go through www.pantechelearning.com or www.pantechsolutions. So you can visit our website, Pantech Private Limited. So thank you all. Thank you for participation. Hope you people are enjoy the session.